Hello everyone. Welcome to EOS Remediation's webinar titled Principles and Practices of Bioremediation. Our presenter today is Brad Elkins, Technical Sales and Support Manager for EOS Remediation. Welcome, Brad.
Thank you. This presentation will be a general overview of the science behind bioremediation and its technique for cleaning up contaminated sites. It'll be sort of a brief overview of the science, but I'm also going to go into details about more in-depth topics such as bioaugmentation and pH adjustment. So let's get started. First, what is bioremediation? Bioremediation is essentially the means of using biological organisms to solve an environmental problem, such as contaminated soil or groundwater. And there's really two components of bioremediation. To make bioremediation work, you need an electron donor and you need an electron acceptor. Now, the electron donor can be a bunch of different things. It could be naturally occurring organic matter in the aquifer. It could be something you add, such as sodium lactate, molasses, or even vegetable oil. And it could also be a contaminant itself, such as a petroleum hydrocarbon, like benzene. The electron acceptor could be a bunch of different things, but in general, they're going to be something more of like a respiring agent, like oxygen, nitrate, or iron. And in the case of a contaminant, would be a chlorinated solvent, such as PCE, which is tetrachloroethene, or TCE, trichloroethene. And there's really two basic functions to make these two come together. There's fermentation, and there's respiration. And so fermentation is the act of actually breaking down the electron donor to get at the molecular hydrogen. And respiration is sort of the act of breathing or making that chemical exchange. You and I do this process every day. When we eat our lunch and breakfast, we eat that food and we breathe oxygen. And microbes in the aquifer do the exact same thing. You give them an electron donor or a fermentation agent such as emulsified vegetable oil or EOS. They break that down, releasing molecular hydrogen. It is then that molecular hydrogen that's actually used as the electron donor and through respiration is exchanged with a chlorine to break down the contaminant. So here I'm showing PCE being degraded to TCE. And when the bug does this, they produce energy. And that energy allows them to do their cellular processes and multiply. Of course, we want this breakdown of something like PCE to continue. TCE is not the end goal. The end goal is actually to take PCE and break it down to ethene. And so here I've shown the pathway. And so this continuation of microbial respiration, where you produce molecular hydrogen, and continually breaking off a chlorine, adding a hydrogen until you get to ethene. That's the ultimate goal. And there's really three types of bioremediation that are out there. Three sort of general fields of in situ bioremediation. The first one is called natural attenuation, and that's where the biotransformation occurs naturally. You have the right kind of bugs, and you have the right kind of carbon source or nutrient source. And in the literature, this is known as monitored natural attenuation, because all you have to do is just monitor the groundwater conditions, and the contaminant will clean itself up naturally over time. The second is biostimulation or bioenhancement, and that's again where you might have the right microbes present, but you lack that sufficient electron donor or nutrients, and so something must be added to the system to foster bioactivity. And there's two pathways within this segment. There's aerobic, which would require oxygen, and anaerobic, which can be utilized anything other than oxygen. And then finally, there's bioaugmentation, which is where you need to add the microorganisms to the system because you either don't have the right microorganisms or you lack a sufficient population. So real quick, sort of a overview. Why would you consider using bioremediation at a site for your remediation technique? The first reason is cost. When you compare enhanced bioremediation to some other in situ technologies, you're looking at a dramatic cost savings. And when you look at the sustainability of that treatment, again comparing in situ bio to other in situ techniques, you get much more life out of the product, out of the technology. Whereas you can only get about maybe 1 to 2 years out of something like thermal or ISCO, you can expect on average to get somewhere between 2 to 5 years of sustained treatment using enhanced bio. Again, the range of contaminants you can use for bioremediation are wide range, a plethora of contaminants. And really what it comes down to is the role that the contaminant fits for that microbial respiration. And so here I have the contaminants broken out into what role they fill, whether it's an electron donor or an electron acceptor, and then of course what you would need to supply to remediate these contaminants. And so on the electron donors, that would be your gasoline range contaminants such as BTEX. And on the electron acceptor side, most commonly people are dealing with chlorinated solvents, but you can also remediate things like energetics such as perchlorate or TNT. You can remediate hexavalent chromium, nitrates. You can even reduce some radionuclides, and you can even control acid mine drainage with bioremediation. And so at EOS, we have several products that would fill this role. On the electron acceptor end, we've got oxygen and sulfate. And on the electron donor side, we have several different formulations of emulsified vegetable oil. So that's the same vegetable oil you would use to, cook food with. We've just emulsified it in water and added some other proprietary ingredients to it that the microbes favor. And then each emulsion has a specific application. I won't go into that into much detail in this presentation, but if you are interested, I would highly recommend you visit our website or contact one of our other technical representatives by calling the number, and I will provide all of that contact information at the end of the presentation. But moving on, I really want to focus on selection factors. So when you're considering using an electron donor or an electron acceptor for bioremediation, what are the key things you need to be aware of? Mostly I'm going to focus on the electron donor side, but I will touch on the electron acceptors. The critical factors for selecting an electron donor are understanding the ORP of the aquifer, knowing how much hydrogen versus acidity is going to be produced from the electron donor, the biodegradation rate and the longevity of that donor, and then finally the ease of injection and distribution in the subsurface. So again, here's my formula. You've got our donor and our acceptor, and of course the microbes are utilizing those to be able to produce energy. What I really want to focus on first is the electron acceptor. So it turns out that there are ubiquitous microbes in the subsurface that will utilize oxygen, and oxygen actually, as it turns out, produces a lot of energy when it's used in this microbial respiration. And so it's preferred. It's the preferred electron acceptor no matter what the electron donor is. Microbes are going to go for oxygen first. But once all that's depleted, then we sort of get this sequence of the bugs like to consume nitrate and then iron and then sulfate until they finally get to the chlorinated solvent or the contaminant of concern. The other thing, and I'll point your attention to the right-hand side of the slide, is if you see the ORP, one sort of, I think, maybe misconception that's out there is that negative ORP and anaerobic conditions are hand in hand. Not always true. You can have still a positive ORP, but be in an anaerobic state. And so it's important to make sure that at your site you're monitoring not only your ORP, but your DO levels. As I mentioned, there is sort of this favoritism of electron acceptors by the microorganisms in the subsurface. And here I'm going to play an animation for you that's going to show what happens when an abundant carbon source is introduced into a theoretical aquifer and sort of the stepwise degradation of electron acceptors. So if you introduce a carbon source into an aquifer, the first thing that's going to occur is aerobic respiration. But when that oxygen is depleted, it's going to go into an anaerobic respiration state. And it's going to start consuming things like nitrate, manganese, iron. When all those are gone, it's going to move to sulfate. And when that's gone, it's going to move into methanogenesis. And it's that range between sulfate reduction and methanogenesis that you're really after for proper dechlorination or reduction of the contaminant of concern. Next is obviously the hydrogen. How much, because we're after molecular hydrogen after all, how much of this hydrogen are you getting per pound of substrate that you inject in the ground? So I've listed various substrates, everything from lactic acid to soybean oil. And you can see on the right-hand side, there's a column called H plus to H2. That's essentially the acidity per molecular hydrogen ratio. And then next to that is the H2 per kilogram. So that's how much hydrogen you're getting per kilogram of product. And you see that soybean oil at the bottom has one of the highest yields of hydrogen per kilogram. This table is a little hard to digest. So what I've done is I've sort of graphically put this table together for you in this bar chart. And again, on the left-hand side, we're looking at the acidity to molecular hydrogen ratio. And on the right-hand side, we're looking at the hydrogen per kilogram ratio. And what I want to put your attention to first is something like sodium lactate. Sodium lactate's a great substrate. It's an excellent electron donor. You get relatively low acidity per molecular hydrogen generated, and you get a modest amount of hydrogen per kilogram. Although, when you compare it to soybean oil, again, you're getting that nice sort of control of acidity per hydrogen, but you're getting a lot more molecular hydrogen per kilogram, an order of magnitude greater in hydrogen. So, picking your substrate is vital. You need to be understand exactly what you're getting per pound of that substrate. When you think about biodegradability, that's really the key. That's really sort of what is going to sort of control that release of acidity. So something that takes a very long time for the microbes to break down is going to have a lesser effect on shocking the system with a pH burst. We've been able to see that in the lab that the microbes take a lot longer to degrade something that has a complex molecular structure, something like chitin or mineral oil. It takes a very long time to degrade. So if you look at this graph here on the right hand side and you see that red line, that's chitin. And you see that it takes a very long time to sort of start releasing fermentation products. And so what we're measuring here on the y-axis is the gas production, so the methane or CO2 production. And that's an indication of fermentation. And so by looking at the chitin line, you see that it took a very long time to start ramping up and getting a lot of methane production. Whereas when you compare it to the sodium lactate line, which is the purple line there, you get a very quick spike in methane production. That's because the material is fermenting quickly. And then it drops off, and it never really recovers after that. And then you look at soybean oil. Soybean oil, it takes a little bit longer, but you get this nice, really slow release of methane over a long period of time. So this really shows that the degradation rate is important for sustained treatment at a site. Again, when you're talking about soluble substrates, essentially there's two processes that occur. There's fermentation and respiration. So with a soluble substrate, you're going to get very quick degradation. It's going to immediately ferment and release hydrogen and acetic acid. And that's okay, because the bugs can utilize that and create those reducing conditions. However, you will not get that sustained life that you need, because these contaminants can take a very long time to degrade. And so by having that rapid fermentation, you're going to need higher reinjections. You're going to need more reinjections to address the contaminant of concern. So your frequency is going to be up, so therefore your project costs will increase. Also, consider the acidity, that with that quick fermentation, you're going to get this sort of sudden drop in pH. And when you compare that to a more slow release substrate like soybean oil, there's a sort of an additional step that the substrate has to take to get to that hydrogen. It actually has to ferment into volatile fatty acids. Those volatile fatty acids can then be further degraded into hydrogen and acetic acid. Sort of the take-home message here is a slower release substrate is going to give you a more gradual fermentation. It's going to give you a more slow, more constant supply of that electron donor, because it has to go through sort of a two-step process. But the problem with these substrates like soybean oil is, how do you get soybean oil to disperse and properly inject in an aquifer environment? Well, that's sort of what EOS is. EOS is really a composition of soybean oil, sodium lactate, which is, a soluble substrate, yeast extracts, and vitamins. And it's this combination of short and long-term substrates that makes EOS highly effective. This has been demonstrated by a third party. This data here on the right-hand side is from Paul Hatzinger of CB&I. He looked at degradation rates of perchlorate and RDX, and he tested a multitude of substrates and electron donors. You see the red line on both graphs, that's EOS. And especially when you look at the perchlorate, you can see that the degradation rate of perchlorate when you use EOS outperforms everything else. And that's a peculiar thing, because when you look at this, you see that he also tested hydrogen. And you would think that if you just gave the microbes hydrogen, well, that's what we're after, so that should work the best. Turns out that these organisms are, well, just like you and me. They can't live off of a simple electron donor source. They need other things in order to perform their cellular respiration and to produce enzymes that they need to sustain their existence. Essentially, they're going to need, fats, the proteins, and vitamins, and EOS provides all of this. And so when you give the microbes sort of this, I'm using quotations, a well-balanced diet, they're going to perform much better for you. The other thing about EOS is it's an emulsion. It's oil in water. And because we've been able to emulsify the oil and produce very fine droplet sizes of the oil, this allows for proper distribution in the subsurface. What I've shown you on this slide is on A, this is a very crude emulsion that was made in the field with just a regular sort of shear mixer or a paint mixer or something of that sort. You see that the droplet sizes, when you compare them to the picture on the right, which is the B picture, you see that the B picture almost looks like TV screen static. You can really see that those droplets are a lot smaller than the ones on the left-hand side. This picture B is actually EOS that's gone through our production in our factory. And for scale, I've put that 10 micron bar there, so you can sort of see the scales of the two emulsions. This is an important concept to understand, the oil droplet size and oil retention. So how likely is it that these soil particles or these oil particles in soil are going to stick or collide and then thus either stay there and not go any further, or they're going to be able to move on and distribute in the aquifer? And so here I'm going to sort of demonstrate this process. I've got a theoretical cross-section of an aquifer. I've mobilized my field crew to the site. We've punched our geoprobe wells into the subsurface, and I've got two lithologic units. I've got a clay and I've got a sand. So if I bought EOS, let's just say 100 gallons of EOS, and I mixed that with water and I injected that in the ground, I could expect to see a certain radius of influence of that material, maybe 10 feet from that injection location. The reason for that is the benefits of it being emulsified are that the oil droplets are 1 micron in diameter, which allows better distribution. EOS has a slightly negative charge on each oil droplet, so that makes them want to stick to the more positively charged fine-grained material of the aquifer. And finally, the EOS is not going to advance until most of the attachment sites in the aquifer are occupied, and then it'll move on. So you know that you're getting this nice even distribution of the oil in the subsurface. But if I took that same volume, that same 100 gallons, diluted it with water, and I injected it into my tighter formation in the clay, the EOS is not going to go as far. It's not going to achieve that 10-foot radius of influence from the injection point. It might only go 2.5 feet or 3 feet. Really, and the reason for that is surface area. Obviously, with a finer material, you've got lower permeability, but you've also got more surface area to cover with the EOS material. And also, the clay materials are going to be more positively charged, so you're going to get more of the EOS sticking to those available attachment sites. So when I deal with a clay, it is not unrealistic that I'm going to need to inject 2, maybe even 3 times as much material in the ground to achieve that same distribution I saw in the sand. And again, this is just all based on oil retention of the aquifer material, I will be able to get away with lower dilutions in a sand versus a clay where I'm going to need higher dilutions. And I can also expect larger radius of influence in a sand unit or a coarse grain unit than I will in a finer grain unit, such as a sand or such as a clay or a silt, excuse me. Finally, I think a lot of people want to know, how can you properly inject EOS? What are the various injection methods out there? And really, the sky is sort of the limit. We do not have a lot of restrictions on how you can introduce this material into the aquifer. You can use everything from direct push technology, such as a geoprobe. You could install temporary points. You could install permanent injection points if you thought you might have to go back out and re-inject over multiple years. And finally, you could set up a real circulation system where you have down gradient extraction wells where you can induce a gradient on the water table, pump the material out, and then pump it back in at the injection location up gradient. So really any of these methods are applicable to EOS, and there are several others out there that I haven't listed here that are applicable as well. The biggest thing about EOS is, and I think a lot of the questions that are out there is, how can you increase your distribution of a substrate? How can you get that proper contact? Because again, this is a contact sport. Well, there's really sort of three fundamental ways you can do that. You can either inject more EOS or substrate of your choice. You could inject EOS, you can inject more EOS or substrate with a higher dilution or add more chase water. Or you can inject your EOS or substrate of choice through more closely spaced wells or through tighter or shorter screen intervals. All of these options are going to ultimately cost the project more money. And really, it's just kind of working with our technical team to understand your site, your remediation goals, to determine which of these is most appropriate. So I'd like to take all of this I talked about, everything from substrate selection, fermentation, and then distribution in the aquifer. And I'd like to share a brief case study with you. This is a confidential site. The aquifer was a sand and gravel aquifer. The water table is about 20 feet below land surface. And this is a TCE plume, so this is trichloroethylene. And it's an extremely large plume, 2,500 feet long. The picture, the sort of aerial photo in the upper right-hand corner of the slide, that's a picture of the site, and you can see that black hashed bubble, that's the plume. And you see the source originating at the far right-hand end of the page and then moving sort of east to west across the site. This client ended up injecting 3,600 gallons of EOS Pro at a 2% dilution. They injected into both the source area, and then they did a down gradient barrier. The other thing they did is they injected, before they injected EOS Pro, they preconditioned the aquifer with sodium lactate. And they also did that in a lot of the hot spot areas to sort of help get the ORP, get that DO down, and start maybe hitting some of those more concentrated areas. This project occurred in 2008 and 2009. Finally, the CAD drawing at the bottom right-hand corner of the slide, that's the sort of layout of the injection wells and then the plume itself. And you can see the green line is sort of that the outer edge of the plume. So let's look at some data. So they injected the EOS. You can see they did this in the middle of winter. There was snow on the ground. And let's look at two data points. Let's look at the source area and the down gradient barrier. First, let's look at the source area. That's the upper left-hand corner. You see that their TCE, which is the red line, started at about 400 micrograms per liter. And once they introduced the EOS, that immediately dropped off. Within about 6 months, they saw no more TCE at the site. However, they did see, which is this sort of greenish yellowish line, they saw an increase in the DCE, which is one of the daughter products of TCE. And they actually saw this increase quite a bit. In fact, you kind of look at this and the mass doesn't really make sense. And that's because they believe that there was some desorption off of the aquifer material. But regardless, almost a year later, they saw pretty much complete degradation of all of the contaminants of concern. They were even forming a little ethane there for a while, but eventually everything just went to zero. And that's really what you'd want to see. If we look at the down gradient barrier, it's a very similar story. didn't start with quite as high concentrations. Here they only started with about 50 micrograms per liter of TCE, but ultimately they saw the same result. They saw an increase in their DCE initially, and then you look about a year to 2 years later, and everything had gone to essentially zero. The take-home message of this example is this engineer saw TCE reduced below the maximum contamination limit within the first 2 years of introducing the emulsified vegetable oil into the ground. The down gradient monitoring well saw the TCE concentrations decline dramatically as well. And they actually observed pretty quick degradation rates on the order of about 40-day half-life. And that's considering the fact that the emulsified vegetable oil is a slow-release electron donor. The last thing I'll mention is that this engineer did not bioaugment. They did not add any of the dihalocoides to this site to promote dechlorination. That's actually something I haven't talked about yet, is bioaugmentation and the introduction of microorganisms into a site. You can see that the plume at this site went away pretty much over the life of the project. It went from that very large plume to essentially this one little green dot here. So a great success. Now let's talk about bioaugmentation. So here's our cartoon of showing the electron donor and the electron acceptor again. We're talking about the same process. You introduce the substrate, it ferments releasing hydrogen, and you get degradation of the product or the contaminant. You see that there are actually multiple microorganisms in the ground that can degrade the PCE and take it to TCE, and here I've listed several. However, there's only one microbe out there that can degrade vinyl chloride, which is one of the daughter products of PCE, and take it to ethene. And that's dihalocoides. And at EOS Remediation, we can provide that bug to you, as well as other bugs that are capable of dechlorination in our culture BAC9. But how do you know if you need to bioaugment? You know, the consultant or the engineer that I showed you in the case study didn't need to. How did they know that? Well, you can always test and measure your microbial population in the subsurface. But another way you can look at it is by your data. If you inherit a site or you've been working on a site for some time, maybe you've introduced a carbon source, maybe you haven't. If you look at your data, if you look at the parent product, so the PCE and the TCE, to daughter product, that's the DCE to vinyl chloride, you'll notice that your vinyl chloride and DCE levels rise, but then level off. They don't decrease with time, and you never really see any ethene production. So that might be an indication that you need to add bugs to the system. Finally, you know, to sort of see how effective a dechlorinating culture can be to a system, the graph on the right-hand side shows a microcosm that was done where 60 micromolar of PCE was introduced into a column, and then the dechlorinating culture was added, and then they monitored and timed the degradation. You can see that within 2 hours, they had complete destruction of the PCE all the way through all of the daughter product steps to vinyl chloride, and then the vinyl chloride was eventually completely removed from the microcosm. And this all occurred within just 120 minutes. So these microbes, these dechlorinating cultures, are very powerful. They have great degradation rates. Finally, the last subject I'd like to touch on is managing your aquifer pH. This is a common problem for bioremediation. Not only are you forming fermentable acids from your electron donor, which I've discussed in length at the beginning, but also every time you degrade the chlorinated solvent, you will release a hydrochloric acid. Theoretically, if you degrade 1 mole of PCE, you will generate 4 moles of hydrochloric acid. And why does this matter? It's well documented that dihalocoides and some other microbes in the subsurface are sensitive to pH. In fact, if you get too high or too low in pH, their microbial activity essentially stops. So how do you control the swings in pH? Well, you could add a base. Here I've listed 4 very common bases that are used. I will point your attention to the the column that says OH per kilogram. Again, just like our substrate, the amount of hydrogen you produce is important. For a base, the amount of alkalinity you produce per pound is very important. And so you would want a base that would produce the most alkalinity per pound or per kilogram that you can get. The other column I'll point your attention to is solubility. Just like the electron donor, getting the material to distribute in the aquifer is critical, because if you don't get it to where you're trying to do your remediation, nothing will happen. So having a good solubility is nice, because then it's easy to inject. So if you look at something like a brucite or magnesium hydroxide, you see that it gives you a lot of alkalinity per kilogram, but essentially has no solubility. Whereas if you look at a caustic soda like sodium hydroxide, you get pretty good alkalinity per kilogram, and it's almost infinitely soluble. The problem, though, with something like sodium hydroxide is that it has a very high equilibrium pH, and it is extremely easy to overshoot your pH if you use something like sodium hydroxide. That's why at EOS we've really focused on magnesium hydroxide. From that table you saw, it gets very good alkalinity per kilogram, and its equilibrium pH is about 10.5. So no matter how much magnesium hydroxide you add to a system, you're almost never going to exceed a pH of about 10.5. But the problem with magnesium hydroxide is that it is not really that soluble. So the question becomes, is how do you make a particulate transport in the aquifer? And so that's really what the folks at EOS have been doing over the last couple of years. One of the most neat products or characteristics of magnesium hydroxide is that it even though it is almost not soluble, the solubility of it is controlled by the pH of the system, so that the more acidic the system, the more dissociation you get, so therefore the more pH control you get. And then when that pH shifts more alkaline, the magnesium hydroxide will just reprecipitate and then stay there for to continue buffering the system. So it has a great longevity. And remember, we're after that longevity for dechlorination. We want this material, we want the substrate to last for years, or we want our buffering product to last for years. So magnesium hydroxide presents itself as an excellent buffer for the subsurface. But how can you make that material transport? And that's what we've been doing. So we've developed two products. We've got CoBuff MG and AquaBuff. And CoBuff MG is our newest product. It's just magnesium hydroxide in a colloidal suspension, whereas AquaBuff is emulsified oil with the magnesium hydroxide suspended. Both of these products will provide a slow release of alkaline buffer. They both have an equilibrium pH of about 9 or 10. And just like our EOS products, they both have a negative particle surface charge, so they will attach to any available positively charged attachment sites. We've seen that the control of pH is demonstrated. Here's a graph that shows a titration that was performed by a consultant. They added CoBuff MG to 2 different site soil and groundwaters, and you see the starting pHs on those were both around 3 to 2. Once they added about 15 grams of CoBuff per kilogram of aquifer material, they got to their target pH, which was around 6. But when they kept adding the material to the system, the pH increased until it leveled off at about 8. So even when they needed double the amount to achieve their target pH, they never exceeded a pH greater than 8. So these materials have a fantastic ability to regulate, control pH with little risk of overshooting. Some things to keep in mind if you're going to adjust the pH of your system is understand what your soil acidity and your groundwater acidity is. Understand what the buffering capacity of your aquifer is. The second thing is understand your contaminant concentrations. The more chlorinated solvents you have on site, the more hydrochloric acid you're going to form. Finally, again, consider that substrate. Are you getting a low acidity to molecular hydrogen ratio? And if you aren't, are you prepared to deal with the amount of acidity you're going to generate during fermentation? And with that, that will conclude my presentation. I would really like to appreciate everyone's listening today. If you have any questions for me, feel free to contact me at my contact information is there. Thank you so much. Have a great day.
Thank you for viewing our webinar today, Principles and Practices of Bioremediation. You've been listening to Brad Elkins, Technical Sales and Support Manager with EOS Remediation.